Thank you very much for the invitation. It's my great pleasure to speak, although kind of on Zoom, for this nice seminar. So today I would like to talk about the so-called applications of arithmetic holonomicity theorems. I'm going to explain the words later. I was first to say that this joint work with Frank Calgary and Vasily Dimitrov. So I would like to start from actually one of the applications, namely the unbounded denominator conjecture, which serve as a motivation to kind of introduce the so-called arithmetic holonomicity theorems, and then I'll give another application at the end. Okay, so let me start from an example. This is a very classical example, even go back to the work of Klein and the data written up in the work of Frick. So the example is that we consider the modulo lambda function. This is a Q expansion with all the Fourier coefficients to be integers. And then, so let me just give a simple observation. The first one is really just unwinding the definition that we say that I'll put 16 out just for the ease of notation. So if we take eighth root, then we see that the power series will still have z coefficients in the Q expansion. But on the other hand, if we take a number which doesn't divide 8, so for instance, 1/3, and let me just write out the first couple of coefficients, try to convince you that there's a general phenomenon about the denominators. And then I'll claim saying that if you really want to try, you could either using Mathematica or your favorite computation tools to see that there's the denominator, which is powers of 3, is getting larger and larger as the power of the Q goes to infinity, which just means that there's impossible to find just the one power of 3, which kills all the denominators. And this is actually the phenomenon about the difference between congruence and non-congruent subgroups. Okay, so let me actually make the general assertion. So more generally, this is an example of a module form. So let me just give a definition of what do I mean by what's the generality that I know about module forms today. So a module form of weight k and level gamma, where gamma is a finite index subgroup of SL2Z. Is a holomorphic function from the up half plane such that, so it has the usual transition law of the module forms. And the second is we need to have some control at cusps. So we say that F is meromorphic at all the cusps. If you really want to insist a weak condition about the meromorphicity at cusps, so based on our proof, we at least need the meromorphicity at one gamma 2 orbit of cusps. Okay, but that's just a technical condition. But we need certain kind of conditions at cusps. And then so, which I was trying to allude to in the example. So in the example part that I was trying to allude to, as I mentioned, the word of congruence versus non-congruence. So is that on one hand, we have just a lambda. So lambda over 16 to the 1 over n. So here n is a positive integer, is the hypermodule of an index n subgroup of gamma 2 inside SL2Z. And actually, it was already in the work of Klein and Frick. They know that such a group, let me just denote with gamma n. Oh, sorry. Gamma n is congruence if and only if n divides 8. So that's why it's like from the naive example we see it's like a finite index subgroup of SL2Z is congruence if and only in this particular example, if and only if like the most typical module form, the Hapton module for this subgroup is like whether the free coefficients has bounded denominator or not. And actually that's a theorem. So let me just give a precise statement. We say that for a modular form F with Fourier coefficient, with Fourier expansion. This is for simplicity. Q bar Q to the 1 over n. Okay, let me just finish the statement of the theorem and then talk a little bit about the assumption. So first is like F lies in Z bar. So in general, instead of working with like Z coefficients, like we work with algebra integers to replace the role of Z coefficients in the previous example. And still tensor Q, namely kind of we allow to use a large number to clean up all the denominators. So F has bounded denominators in the free expansion if and only if the largest gamma such that F is of level gamma is congruence. Okay, so between these two directions, there's a classical direction, namely true implies 1 is the classical direction, which you can start from Heck theory and plus some additional argument from, say, for instance, from Shimura's book, that once you decompose a module form into a finite sum of Heck eigenforms, then all the Heck eigenforms would have like the free coefficients to be algebra integers. And then the relatively new direction is 1 implies 2. This was conjectured by Yunqing and Schwanton Dyer, and recently proved in joint work with Caligari Dimitri Fenn. Okay, so let me go back to a little bit of details about the assertion. So first is like, why do we assume F has like free expansions to be algebra integers? Sorry, to be algebra numbers, is that because like we have all the like modular curves coming from like H quotient gamma to be where gamma is a finite index subgroups to be like ramified cover to the J9 ramified at 3 points, which are like rational numbers, and hence we always have a Q-bar model of the module curves. And then for module forms, these are like global sections of certain line bundles, which are also defined over Q-bar. That's why we can always like find the Q-bar basis for these like for module forms, even though that we're talking about module forms with like from the definition, it's just homomorphic functions. And the other thing that I want to say is that the question, so let me just go back to the example and say something that we still haven't been able to prove so far, is that from the example of the Klein and the Freak, we notice that only 3, if we look at the lambda third root of lambda example, that we notice there's only kind of the prime 3 which show up in the denominator. This is a phenomenon which is true in general, that given any finite index subgroup gamma, it was already observed in the work of Artkin and Schrontendyer, and the proof was written down in a paper of Stroh, where they say that if you give a level gamma, there's only a finite set of primes where you would expect the like denominators to happen. And if you want to have some extra, okay, let me make a remark. If you want to have some, in quotation mark, extra information about where the like finite set is that, so it depends on how much you know about the non-congruent subgroup gamma. In the thesis of Will Chen, he gave like modular interpretations of like non-congruent module forms away from finitely many primes, and he also proves that like the denominators do not show up in away from that finitely many primes. Although kind of like there's some extra algorithm that you need to put into to relate a group gamma to certain modular interpretations. Okay, so this is the statement of the theorem. And then I would like to give a very sketchy proof of the theorem in order to kind of motivate the discussion about the arithmetic holonomicity theorems. Okay. So first, it's a classical reduction step that we can reduce to weight 0. And it depends on your preference. You may further reduce to z coefficients module forms or work with a more general arithmetic holonomicity theorem. That's basically a choice. And then the next thing is that we have two kind of sets. And then the classical direction tells us that the set 2 is contained in set 1. And both we can actually make them into vector spaces, and hence we can count that dimension. But in order to count dimension, we need to first put some extra conditions to make them finite dimensional. So we fix n equals to, this is so-called the Wolfart level, which is the LCM of all the cusp widths of gamma. Sorry, I remember one thing that I forgot to say, is that in the statement of the theorem, you may notice kind of a discrepancy between the definition of module forms and another extra assumption saying that somehow that we put infinity as a special cusp, namely saying that at this cusp it's holomorphic, but it's really doesn't matter, as that you can always use the lambda function to just adjust. The lambda function would at worst introduce extra poles at some other like cusps, but it definitely kind of like multiply a lambda function doesn't change the phenomenon whether it has like bounded denominator or not in the Fourier expansion. Okay. And then so we fix a cusp width so that we can count the dimensions. So we count the dimensions of the vector spaces spanned by 1 or 2 over Q lambda. And then so we already know that 2, so I'll say the vector space of 2 is contained in vector space of 1. And moreover, we know that, so it's the work of Wolfart. The LCM is called the Wolfart level is because that this would imply if it congruence, so gamma congruence plus LCM divides n. So LCM of the cusp width divides n implies that gamma contains gamma n. So that's why we can use gamma n to count the dimension. So this implies that dimension of 2 is, roughly speaking, the index of gamma n inside SL2Z, which is roughly n cubed as n goes to infinity. So we have a asymptotic of one direction. And then we have a key step is how do we say something about the dimension of 1? Is the dimension of 1 is at most n cubed log n. The input here is a couple of things. So first is like arithmetic, first is the arithmetic holonomicity theorem, and which is actually refinement. I'm going to explain all these in a minute. Refinement of the so-called algebraicity criterion of event J, and then plus some, I'll say plus some complex analysis is, I'll put complex analysis at this moment and explain what's the complex analysis input into it once we have, like once I say the precise statement. Okay, so now it's like we have an upper bound of the dimension of 1 and we have a lower bound, which is actually a precise estimate of the dimension of 2. And we want to prove these two things are the same. And then so the last part of the proof is a periodic input. Which says is like if we have a modular form, which is counterexample of level n, which lies in 1 but not 2. And then if we do a change of variable, so like it doesn't change the Fourier coefficients rather than shift it. And then this is kind of a heck translate, and hence it's also still not congruence. So we have another one. This, okay, so let me, for simplicity, that for P doesn't divide n. So this one will have level P times n, and F tau over P doesn't like seeing the ring generated by F and the congruence forms of level P times n. Okay, so this is just like if we have like one counterexample, then we would have many counterexamples which are independent from the previous ones. And then one can actually just, this will imply, I will not do the exercise of prime number theorem, but I'll just say this will imply contradiction. And if such F exists, because we can count, say, up to level m equals to n times the product of p up to a very large number, p doesn't divide n p. So for each p is that we have extra counterexamples, and on the other hand, we still have kind of the upper bound and lower bound. So this is exercise from prime number theorem, which I'll not go into the details. Okay, so that's kind of like the very brief sketch idea of proof, which says it's like we have lots of input from module forms, and then plus something that I blackboard as the arithmetic holonomic theorems. And in order to kind of give a meaningful statement of the arithmetic holonomicity theorems, I would like to give a little bit history of the background of theorems in this direction. I'll say a brief history of in order to save time, I'll start from the fancy theorem. So it goes back to the work of the Bro and the work. Which says is like if we have a power series with only finite many primes show up in the denominator. And then if we consider for each V is a place, both Archimedean and non-Archimedean, we can consider the, I'll put a prime because it's different from the usual convergence radius. So it's the V-adic radius of meromorphy of F. Okay, so the usual convergence radius is the radius such that the largest disk such that the function F is holomorphic or analytic, and then so we can weaken this condition by saying that we only assume it should be meromorphic on the disk. And then if the product of all these radius is strictly greater than 1, then F is a rational function. So IE is like F lies in, let me be lazy, just say Q bracket X. Okay, so if you replace the radius of meromorphic just by the usual convergence radius, and then you see this is an easy theorem just from the product formula. And the work is here because he uses to prove the rationality of zeta functions for smooth quasi-projective varieties over finite fields. And then there's one natural extension that one would expect is that instead of talking about just the disk, we can talk about something looks like a disk. So that's the work of Claudia and the Bertrandis. So when there's two people, usually the first one did the case that assume, for instance, it has Z coefficient power series and work with the Archimedean place as a separate place, and the second person just work with all the periodic places. And the work of Correa-Berchandus is like they allow, like I'll only state a easy version. They allow more generality. So I'll state a special case saying that they consider replace RV prime by the following is like we consider phi v to be a disk maps to CV such that I'll put it's an injective map such that F is a meromorphic function on the image of phi v, or in other words, it's like we can say F composed with phi v is meromorphic on D01. And then we replace by the absolute value of the derivative at 0. Okay, once you replace by RV by this kind of, you can work with more arbitrary regions. The statement still holds the same. It's like if the product is strictly greater than 1, then it's rational. And then it may look a little bit artificial that when I state it this way, we assume that this is an injective map, namely it's isomorphic with its image. So what if we drop this condition? So that's actually the work of Ivan J. And again, it's kind of a special case. What he proved in general is that, there's an identical condition is like we assume phi v equals to identity for almost all v. And then we just allow any phi v from the disk to CV such that F pulled back by phi v is meromorphic on the disk. And then, so if the product, and still with the identical assumption, it's like identity away from finite many primes. If the product is greater than 1, then F is algebraic. Namely, it's like F is algebraic over QX, or like 1F powers of F are linearly dependent. Okay, that's not just a reformulation of the statement, but actually that's how the proof goes, is that the work of Ivan J actually using the properties of phi gives an effective upper bound on the dimension spanned by powers of F. And that's why kind of like this statement, let me just go back a little bit. This statement and our key step has something to do with each other, because it's like the assumption in 1 is like you have a power series with like certain Z expansions. And then in the case of weight 0, we reduce everything to weight 0. So we know, okay, on one hand, we know those are algebra functions. So we just want to compute the span like of like all these like algebra functions. And that's why kind of like one would expect that a refinement of the work of Ivan J would actually give you a nice estimate of the dimension. And the one thing I would like to mention is that this is indeed the case, and I'll just give a statement of a special case of our bound. There's no slightly different from the ones that we have in the paper, but like I'll say more about proof later. Okay, so if we have Fn to be elements with Z expansions, and if we have, let me only do the Archimedean place. Sorry, one thing I forgot to mention is zero always maps to 0 in all these maps. I here state like the pullback to be holomorphic just to be compatible with what we wrote in the paper, but you can actually like loosen the assumption to be meromorphic and assume the derivative is greater than 1, then note that having Z expansion is the same as saying kind of like you just pick the trivial disk and the p-adic convergence radius is at least 1 for all the primes. And then the dimension over Qx of the span F1 to Fm is smaller than, no greater than 2 times the integration, which is actually the nonlinear character over log phi prime 0. And we'll have a different looking bound, which is, so basically you can take the minimum of these two bounds, depends on how one could actually compute the constants. I'll put it as an end. Okay. So let me make a quick remark. This is not the exact version that we used in our proof, but I'll make a quick remark how this is related to the proof. So first is like I said, we already have them to be algebraic functions with respect to the lambda coordinate. Like we consider like all the module form with 0 and assume that they all lies in gamma 2. So they kind of like are algebra functions over the lambda coordinate. So, and that's why this is actually the dimension bound that we're going to bound. It's like we're going to bound the dimension over Q lambda. So we're going to take X equals to lambda, but we may not have this condition unless the cusp width is like divides 2. It's like we know that lambda has an integer Q expansion. So if our Q expansion is just the Q, where Q is e to the pi I tau, and then we can actually translate integer Q expansion to an integer lambda expansion and apply the theorem. On the other hand, but in order to actually count all the module forms, then we actually need to do a change of coordinate in the sense it's like lambda is not good enough for the like local Q expansion. We need to take lambda to the 1 over n, but that's introduced the extra denominator n that we need to take care of. But essentially, that's the technical detail that I'm ignoring. Essentially, that will get such a bound. I mean, in the sense the extra n that you put into will be compatible with this. I'll make a remark is that in our, sorry.
Yunqing, sorry, I have a question. In
yes.
your theorem, the coefficients were also, they were not just rational, right? They were actually algebraic, weren't they?
Yes, that's a great question. Okay, that's the thing that I said. I said you have a choice. In the sense is like either in the proof you reduce everything to the Z coefficient case by just taking the Galois summation of all the like Galois twist to do the summation to the trace, Or here I just state, actually, let me just start from even the history, is that here for simplicity, I state everything in Z. You can replace Z by a ring of integers of any number field in all these statements, and then all the places. Just remember to get all the places, and then everything will be fine.
Okay, thank you.
Yeah, thank you. And then another remark I would like to make is about the constant true doesn't really play a role in this proof. It's like we just need some number, and that's why in our original proof it's true. Sorry, it's E. And then we get the constant true, which is like inspired by, so let me actually put this as a remark here. It's inspired by the recent work of Bost and Schaus. That's a paper on ICAF last year. Is that in this particular case, they actually interpret everything in terms of certain like arithmetic intersection number on certain formal arithmetic surface and give a more geometric interpretation of the bound, and they actually give a better bound than what we have so far. But okay, since I want to talk about something else, so I'll refer you to their paper for the exactly better bound. But better in the sense is like it's smaller than the bound that we give here. But for the purpose, as far as we can tell, it's like asymptotically it's up to a constant. So for this proof, it doesn't change much. And inspired by their work, we kind of revisit the slope method of Bost, and then we come up with just a more classical slope method proof, which gives the constant too. Okay, so I would like to say a little bit how one actually use the bound. Let me choose a different color. So how we use the bound is the following, is that we have, so that's the complex analysis in the following way. Okay, so first is like, if we only have a module form without knowing the weight zero assumption, we would only say, we can have the Q expansion, and that gives you kind of like, if you look at Andre's definition, that gives you like something Archimedean radius equals to 1, but that's not good enough. So what we are going to do is the following, is that, so we still back to the assumption that we have like the N equals to the LCM of cusp width. And then what we have is that actually, so the cusp width actually tells us what is the local monodromy of the covering from the, so this actually controls, so if I have F star, sorry, the modular curve, the compressified modular curve to the lambda line, which is like P1 minus 0, 1 over 16 and infinity. So sorry. This is given by lambda over 16. And then we know that kind of all the local monodromy in this ramified cover is divided by like N. And that's why we could locally, so locally we can have, if we work with lambda over 16 to the 1 over N, we resolve local monodromy at cusps above 0. And so which means what we have is the following, is that we resolve the singularity at 0, and hence we can actually work with just hence we'll say that we take phi equals to, in quotation mark, we have, so P1 now is like, we take the nth root, so we minus 1 over 16 to the 1 over n mu n and the infinity. But now 0 is no longer a singularity, we already resolve it. So phi would be the universal cover. So basically, it's like we know the local monodromy is just 1 over n. We take the we take the nth roots to resolve the local monodromy, and hence we can extend. Here we use like we need meromorphicity at least at one of the cusps so that we can talk about the like local monodromy and then like resolve at least one of the singularities, and that gives us, because it's like we do have the lambda map, which is not a universal curve, lambda to the 1 over n, which has derivative equals to 1. So that guarantees that the universal curve has derivative strictly greater than 1. And that will give us, so one thing is like you can actually explicitly compute. Okay, so one remark I want to make here is like if you look at this form and you want this to be as small as possible, then you would like to have the denominator to be large, and that's why kind of in practice oftentimes we take the universal current because that's without extra information that's the best we could do. And hence this will give us, so this will it's like this will give us n to the -3 in here. And then okay, so we cannot take the, I put a quotation mark is because we cannot take the universal cover things kind of like this here, we assume it's to be kind of holomorphic on a small neighborhood of the closed disk, but that's only one natural thing you could do. It's just you shrink this one a little bit, take a small like radius r goes to 1, and then do the integration there. And things I already mentioned, this is the nonlinear character, and hence kind of like a more uniform version of the classical second main theorem of the nonlinear theory actually help us to control the top term, which gives the extra log n in the estimate. Okay, so that is a very vague explanation on what is the complex analytic input. I'll be happy to expand more details, like if you have questions after the talk. Now let me give another application. So in the sense it's like, as I put the title to be applications of arithmetic holonomic theorems, that I would like to give another application, which is like not in the situation of the unbounded denominator conjecture, but something else. Okay, so instead of give you the statement, I would like to give the application first and then modify the statement. So this current bound is not good enough. We're going to have another bound, which is more general. Okay, so I'll just say irrationality problems. And I'll just give one example and say what else one expects to do. So since this is a number theory seminar, so I'll just jump to saying that zeta values and periodic zeta values are very important. And so let me actually first give a definition. So the periodic zeta value is given by just you interpret the classical ones in a limit behavior. So we have so we use the classical zeta value, but we remove the periodic part. And this is taking the limit inside QP. Okay, but what we are actually going to use is this is the constant which show up in certain periodic Eisenstein series. And what was known before is I'll just mention one work. There are many works kind of like multiple periodic zeta values, linear expansions from them, but I'll focus myself just on the most relevant previous work, as in the work of Frank's paper in 2005, where he proved that the two-adic zeta value at 3 and the three-adic zeta value at 3 are both irrational. And his proof was like inspired by the proof of Berkeley's using module forms to reinterpret April's proof of zeta 3 to be irrational. And then let me just repeat the idea. Okay, so first I'll give the next one. So if I said kind of like I mentioned, these are the two most relevant examples. So our theorem is actually the next case. We can prove that the two-adic zeta value at 5 is not rational. And for the first step of the idea of proof, we'll just kind of like copy Frank's proof, saying that we work with a periodic Eisenstein series. Here we work with the one with weight -4, 4 equals to 5 minus 1, which gives the zeta value as a constant term. So I would like to actually write out the Frick expansion because I want to explain. So this is an element inside Q bracket Q. If zeta to 5 is rational. So we prove by contradiction. And then, so it's kind of similar to the previous business. How do you kind of expect to have anything meaningful that you can apply? Certain refinement of algebraization theorem is we first make it with 0, and then we look at it with respect to the like coordinate of some Hopfian modulo. And that's what we do, is that we pair it. So we pick a classical, you can pick any classical weight 4 Eisenstein series. Here, the only assumption is we want it to be inside. Okay, so you pick any classical ones, you end up to have like essentially the expansions in the Fourier coefficients and on x0 too, because we don't want to introduce extra level. And then we pick coordinate, sorry, P1. And then we pick coordinate x q to be delta 2 tau over delta tau. And this one still has very nice Q expansion. Okay, then we are going to write the product of these two things, which is virtually weight 0, as a power series in X. And you can see that it has Q coefficients if we assume for contradiction. Now it's like what we have is the Archimedean, we have the convergence radius is like we have RP. This is just the convergence radius is at least 1 for every prime P. And then we have, so let me just copy it from Frank's paper, saying that the classical work of Coleman and Bezos, which are over convergence, and based on the computation Frank did in his paper, shows that we have the two-adic, it's a two-adic Eisenstein series, and so this one is greater than 2 to the 12. That's the disk where you kind of extended over the whole kind of supersingular region, plus the original ordinary disk that you start from. And then, okay, that's the moment that we really want to use the so-called the previous like bounds and the criterions. And so we look at what we have for the Archimedean part is like the best R infinity that we can take is 1, just using the Q expansion. But like one thing that I'm lying here, which is going to be important, is that we don't only have finite many. So if you are now, let me just kind of get back to the notes a little bit more. If we just looking at all the histories here, we always assume that we have only finitely many primes show up in the denominator. Well, here, if you just kind of like do the computation, and then you will see that we have actually infinitely many primes show up in the denominator. And the problem with infinitely many primes show up in the denominator is that the convergence radius doesn't actually describe the prime by prime convergence radius, doesn't describe the total kind of like behavior of the denominators. And then let me just saying that we introduce another term. I'll call it tau. So in Andre's book, he introduced a tau invariant, which is going to kind of measure what the behavior that you have infinitely many primes show up in the denominator. And in this case, tau is equals to 5. Which you can actually do the following. Is like I said, if you assume everything have like analytic kind of like behavior on all the disks, and then the classical broad work is just a exercise using the product formula. And then when you do the exercise using the product formula, you would actually change 2 limits, because like when you do product formula, you're talking about like product for all the places as n goes to infinity, and on the other hand, you want to group up each prime. So you exchange the 2 limits, and the exchange of the 2 limits when like both limits are infinite will give you some extra term, and that's the extra term which you like eventually use as tau invariant. So okay, now we have every information we needed, and then the so-called, I'll say the arithmetic holonomicity theorem in this case is saying the dimension. So we still consider all the f's which satisfy the same convergence condition, same denominator condition, then the dimension is smaller than, so let me just go back to the dimension here. So this one is that we have the log of the sup norm with derivative on the bottom. And then I'm just going to copy this bound, but put it more addetically. So we sum over all the places. And then we have log sup over the derivative at 0. Here's the difference. So we put a minus tau here. It's like in previous algebraic condition, and there's no extra terms introduced when you kind of switch the 2 limits. So there's nothing to be put here, but if we do have certain condition, we need to put something here. Okay, and then with all this information, oh, great. With all this information, now we can actually try to get a dimension bound. And so I'll say it's like, we want to get a contradiction. So we need some lower bound and we need some upper bound. So let me first talk about the lower bound part. Is that what we have is like, since we have weight equals to 4 and the negative 4, so we can actually conclude that one f, so f is this kind of, you put these Q expansion into the coordinate of the Hopton module. The derivative of f up to the 4th derivative of f are linearly independent. So first is like we no longer take powers of f as the classical criterion of even j, is because if you take powers of f, you could expect that the denominator measure is actually going to get larger. So for instance, let me give you an example, like log 1 minus x, if you take the Q expansion and you will have this tau invariant to be 1, and you can take the square of it, and then the tau invariant will be like 1 plus a half. So if we look at the bound here, it's like we really don't want this one to get larger. Okay, so one thing I forgot to say is like this bound only makes sense if the denominator is positive. It's kind of the similar condition as, let me actually put, if we have okay, so we want the denominator to be positive for everything to make sense. And that's why we don't want this tau to get too big. And then to not get tau big, one thing that you could do is like taking derivative is not going to change the convergence radius and increase the denominator. And that's a nice thing that we could do here. And on the other hand, so this is the lower bound. So we know that the dimension would be at least 6. And on the other hand, let me just draw a picture without give you the precise number. Is of course, we're not going to take the total Q expansion because then this part like will just blow off. That's too big. And then what we're going to do is like we just pick phi infinity to be that this is our Q disk. And then we pick this region. So the coordinate here is like 1/7. This is 0. So basically it's like we pick R infinity to be first, so you do the Riemann map to make this disk into D01. And then we take the whole thing to the P1 with P1 isomorphic to X02. And then the way why we pick this disk is that you see that on this direction, that this phi infinity is getting larger and larger on this direction because it blows up at this cusp. And that's why we want to like take as small as possible, but still have, in this case, we'll have like R infinity to be 1/4. So we still want something which is to be not too small so that this one would be positive. And then just everything is computable in this case that we have dimensions strictly smaller than 6. And these two implies the contradiction. So we know that zeta 25 is not rational. Okay, so let me just make a quick remark about what's the difference between this proof and the previous proof in Frank's work, is that in his previous work, that essentially he's doing kind of the easy version of Berkeley criterion where he just play with the convergence radius, like the classical version, as many classical proofs of irrationality, that you have a very nice kind of approximation, and then you compute all the convergence radius, do the simple kind of product formula like estimate, and then get the contradiction. And then what we do is like, okay, so from Berkeley work to NJ, as we know that if you want to kind of make the radius larger, you just drop the assumption that you want to work with disk. You can work with other region, or furthermore, you can just work with like just a map from the unit disk to your coordinate. But something gets kind of lost here is like, in the classical work, you just get something is rational, and then you just get the contradiction immediately, because all these like power series you construct for all these like rational approximation are never going to be just a rational function. So that contradiction goes immediately. But in our case, it's like that Andrews algebra criterion, you get something algebraic. While here we get something which satisfies a finite order differential equation, because I said taking derivative doesn't change all these convergence phenomena, but then it gives you an upper bound of the dimension. So one somehow wants the upper bound and the lower bound, which somehow coming from geometry or other ways to contradict from each other. So that's all I want to say. Thank you very much.